the last presenter before lunch, but remember, I'm holding these. No flag, no lunch, okay? Do I have 20 minutes or so? Okay. Again, I'm a practicing engineer. I've worked at Caltrans for the last 30 years. I've witnessed 2 of the big 3 earthquakes. I've been through Northridge, obviously, and the Loma Prieta 1989. I was not around in 1971, but I need to present all those 3 earthquakes to you to see how much we learned, and to see and to be able to project into future and be able to make some statements about adequacy of our bridges for the next big earthquake that's going to come along. Okay. Now, California and Caltrans is the only DOT that writes its own seismic code. That's very important. FHWA, the feds, have trusted Caltrans to obtain an exception from all seismic requirements from all other 49 states, and then be able to write its own code. And the reason that happened is because Caltrans and California was most at risk of earthquake, and it started earliest after 1971. And then hustled and put together code, something called seismic design criteria. How many of you are familiar with that, SDC? Okay, so I'm going to give you a little bit of history of it on how it developed. Let's see if I have a pointer here. No pointers? Oh, can you hear me back there, by the way? No pointers, okay. I'm going to be talking about 3 major earthquakes and how we learned about confinement, continuity, balance. That's my take of all the things that we have learned. Again, I'm highlighting those 3 items, and there are a bunch of other things that are, in my opinion, relatively minor to this. And after you do your 1 billion analysis at Berkeley, you come to Caltrans, and you only have to meet these. That's it, 3 small items. Okay. San Fernando earthquake, a lot of damage, pictures were shown here, and from that earthquake from 1971, Caltrans learned about confinement. How? Because of this. You see bottom of that column? That's called elephant's foot, okay? You see the picture above? The same as the picture below, okay? The picture above is 1994 earthquake, picture below is 1971 earthquake. So, by the time Caltrans started retrofitting after the 1989 earthquake, we did 20,000, we had 26,000 bridges to deal with, and we retrofitted approximately 2,000, but we did not get to this one above, and that's La Cienega, okay? And we were lucky because there were those storage facilities that held up the bridge. Otherwise, that bridge would have completely collapsed. So that's why there were losses after 1994. 57 was mentioned, but on Caltrans bridges, unfortunately, just 1 loss, and that was a highway patrol. Okay. So we were lucky here. So the picture on the left shows our practice before 1971. We used to hold the core of the column with hoops or ties with a lap, meaning that as soon as the cover was lost, the lap will open. You see that on the picture above? The confinement has just opened up. Okay. So we needed to improve on that, and we have done since 1971. We improved it tremendously till 89, and after 89 we even bumped it up further. And you see the picture on the right, that shows a column cage, and you see the amount of confinement on it, the hoops, the number of hoops. And the hoops are now what we call butt splice continuous. Hoops are welded with ultimate splices, okay? Meaning that you pull on that splice and you break the bar, not the hoop. I'm sorry, not the weld. Okay, so picture below again shows the amount of confinement that we are adding. Okay, and here's an example of an actual bridge the column in the background, you see how much confinement is sticking out of it. We put that part of the cage into the superstructure to provide continuity, which I'm going to talk about. Again, picture of 1971, you see that column did not have much confinement to hold. We were lucky again, that bridge did not collapse. It was very close. Okay, so the thing that you got to meet, common sense engineering, it says delta capacity, displacement capacity should be greater than displacement demand. Common sense. Earthquakes demand deformation. Okay. If your structure, doesn't matter if it's a bridge, building, or whatever, if it can provide deformation capability, you can go through the earthquake, not collapse the structure. Okay. You may have to retrofit or replace the structure, but you can prevent loss of life. Okay. So that is in the seismic design criteria section is given, so we have to meet that. How do we do that? Well, we have to quantify the amount of confinement. The more confinement you put in a column, the more displacement you can get out of the column. Okay. We build small scale columns. We really cannot build the 6 and 7 foot columns that easily in the laboratory. You'll see we have limitations. So on these columns, we push and pull. And if you see the picture above, on the left, this is courtesy of UC San Diego. You see how much displacement we are pushing into those columns, and pictures below show the bottom of the column, and we can quantify, we can put a certain amount of confinement into the column, push, pull, figure out the amount of displacement capacity, and then repeat that and quantify that. And Caltrans has done that. We have used models from various universities, but we do have a model in our seismic design criteria. Okay. The picture on the top right, that's a hysteresis. That shows the performance of that column. The fatter and the bigger that hysteresis is, the more energy absorption capability of that column. Okay. Okay. The second earthquake, Loma Prieta, 1989, that was very bad. 40-some lives were lost at Cypress Viaduct, and at the Bay Bridge there was a loss of life, several losses. And this is a famous Bay Bridge where that piece in the middle, the 50-foot piece, fell. We were lucky because it did not punch through the bottom deck, and it did not go through the tower, because if he had done that, then the spans on both sides would have come down. Okay. Now, this bridge was designed for a 5-inch lead on the left-hand side of that failure, and the slab, that floating piece slab, was sitting on it 5 inches. Okay. Now, engineers back in 1930s, when they designed this, I believe they designed it for 6% of G, 0.06 G lateral force. That's more or less the same amount as wind, comparable to wind. They couldn't imagine what kind of movement we're going to have on big bridges like this. Okay, and it turns out obviously the displacement demand is much larger. Even on the new Bay Bridge, the estimate of displacement demand is much larger than the 5 inches. Obviously it was not adequate, so it unseated and it dropped. Okay, as you see here, in the 50s and 60s, you see that hinge, that expansion joint up there in that superstructure. That was a typical design. It was designed for 6 inches, and with shrinkage it would be really effectively 4 inches, and as soon as you shake the bridge, this joint will open up and we would lose one side of the bridge. Okay, so that was typical, and then we have a retrofit solution for that. We get inside the box and we put pipes through, and the restrainer cables we did for a period of time, but now there's the best solution. We put a pipe through, so if it comes unseated, it sits on the pipe. It doesn't fall down. Okay. The worst structure was the Cypress Viaduct. This happened because there were joints in the columns. Okay, there were 2 joints, one at the lower level, one at the upper level, and out of the 2 column bends, there's a column that you see and a column on the other side of the bend. Out of the 4 joints, there were 3 of them that were pinned, And the reason they did that, it was because of pre-stressing needs. Again, service performance dictated those joints, and those joints did not hold, and you see the pictures in here of all the failures. What do we do now? We have no choice but to build continuous cages. These are column cages. You see how tall they are, how difficult they are to pick, and it is dangerous to pick this, but again, we have no other choice. We have to provide continuity for our cages, okay? Our structural elements cannot have too many breaks in them. The better the continuity, the better the performance during earthquake. This is from the New Bay Bridge. The picture on the right, on the top, that piece is going to be lifted, put on the piece on the left, and the two are going to be coupled together by means of what we call ultimate couplers, and that's the one right below, right there. Okay, those are again developed by specifications that Caltrans developed. Ultimate splices was the requirements that was invented at Caltrans, and since then it's picked up. A lot of people are now using ultimate splices, and those are splices, mechanical couplers that if you pull it, you break away from the coupler. You break in the bar, not the coupler. Okay, so continuity, we put them, as we learn from it, we put them in our seismic design criteria. We have minimum standards now for our seats, okay, 30-inch at abutment, 24-inch in the superstructure. We're gonna bump that up in the next release to 30 inches to buy even more insurance. And then in the cast and plate box girder bridges that Caltrans typically builds, we provide enough continuity. We are comfortable about that. Precast is a new phenomenon with what they call accelerated bridge construction. We have to build bridges faster and faster. To do that, we have to use precast elements. And to do that, we have to provide better continuity, because after all, one of the problems in Northridge was that if you put beams on columns and don't connect them properly, you shake them, you're gonna drop them. So joints become very, very important in precast bridge systems. And what we learned, okay, we thought that we had figured this out before '94 Northridge earthquake, but that taught us a lesson on balance. And I'm gonna focus on this. I'm gonna show you what that is, okay. This is the State Route 14 I-5 interchange, okay. The picture that you see here actually is from San Fernando earthquake. It's a 1971 earthquake. The reason I'm showing this again is because this location was hit again in 1994. Okay, and the picture on the right shows the 1994 earthquake collapses. I saw today pictures from Professor Bray that had that in it, and the picture on the left has become a symbol of bridge failure after Northridge. A lot of people are using that picture, and the funny thing about that is that the bench stand up and the superstructures sheared off completely clean. Okay. And it was puzzling for a while. A lot of people looked at it. UC San Diego, Professor Priestley and Seismic looked at it. And after a month or so, the conclusion was that if you look at, you see the abutment in the background up there where the car is parked on it, right there. At that abutment, okay, there was a loss of elevation, and people were puzzled. Why is that drop there? And then if you look carefully, the picture up and on the right shows a completely crushed column. Okay, and the picture on the top left shows the detail of that, and the picture below shows that there is a loss of elevation. There was a column far back, just very close to the abutment, but it was a very short column. Okay, much shorter than the other bends. Therefore, when the bridge moved longitudinally, the short and stiff column took all the shear, failed in shear, okay, and then superstructural came down and started pulling on the rest of the bridge. And that pulling caused a hinge 2 spans over to come unseated. That came down. Once that came down, the superstructure that was connected to this bend on both sides got kinks in it. Both sides were down. So those sheared off, and that is the picture, and that's how we learned about balance. Again, simple equations. We are asking our engineers to balance the bends from each bend to the next one. You cannot deviate more than 25% change in stiffness. Ideally, the best bridge is the one that all the bends are balanced, and during earthquake, all participating, they go through the same displacement, okay? But anyway, reality forces us into some compromise, and that's within these equations, okay? So we are very careful not to do these things anymore. We see the lower picture, K2, K1, that short column is gonna be in trouble, okay? So, what are we doing with our existing columns? Unfortunately, you cannot change the balance on existing columns. It's whatever it is, what it is. So we jacket it and provide as much shear capacity as we can. Jackets work both for confinement and shear capacity. Okay, what is the proof in our practice? We build large column shaft. This is a 6-foot diameter, actually tested by this university. And we are abusing that column, pushing and pulling on it, and at this point we are not holding it with the cables, we are actually pulling, meaning that there is some moment capacity at the base of it. If you look at the base of it, you see that plastic hinge, okay? So there is capacity left in there. So there is a proof that that column can go through that much displacement, 100 inches or so at the top. Very ductile column. This is a large size research that courtesy of UC San Diego, 250 tons, 500 kips of dead load on it, and the framing, the red framing is to catch it. And we did this 4-foot diameter full-size column, and it went through several earthquakes. Earthquake number 3 was the design earthquake. It did not fail at earthquake number 3. Had to go earthquake number 5, which demanded twice as much displacement as the design earthquake. It did not fail again, but all the way to earthquake number 10 and eventually stopped. And here is the shaking. This is the design earthquake. Okay. And then we're going to see the same earthquake, but we are now looking at the base of this. Oops. We are looking at the fixity of the column at the bottom. So you see there is a lot of conservatism in bridge practice. This was the design earthquake. Theoretically, on paper, we were supposed to see a lot more damage than this. Okay. Okay, this is the twice the demand, meaning ductility of 8 out of the column. Again, we are looking at the bottom of the column here. Okay. And finally, this is the last earthquake. Luckily, all that conservatism is going to pay off in future because, as it was said this morning, the demand side, the ground motion side is being studied, and everything, the demand is going up, 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 and then we're going to have to meet it with reserve capacity here. Okay, so what is the proof in our practice? You saw some laboratory tests, and I'm going to show one earthquake. This is the Napa earthquake. This is not quite the proof that we need because this was not big enough, okay, to test all of our systems. This is the big Napa River earthquake, Napa River bridge that you see. It was built in late 60s, and the columns were rectangular section, not much confinement in it. Luckily, this was retrofitted. You see those jackets, round jackets around the columns? Okay. Full jacketing, full rebuild of foundation and superstructure. A lot of money spent there, but it paid off. You can see the one on the left and the right, the difference. And it paid off because even though it moved 6 inches transversely, inch and a half longitudinally. There was no damage to the bridge, and we put service a couple hours after the earthquake. It was very successful story. Here's another bridge, Sonoma Creek. This is before retrofit. You see the pile extensions, they are also battered. We are asking for trouble because when you batter piles, you push, you're gonna cause a lot of shear on the battered piles. And it was retrofitted with this, you see the 4 large pile column shaft extensions on either side of the old bend and rebuilt bend cap. You see that? This is the same bridge rebuilt with that type of a retrofit, okay? And it survived after all. It survived after the Napa earthquake, no damage. Again, was put into service immediately. An example of a bridge that took damage. This is not the Caltrans bridge, but another agency. If you look at the top, these are again pile extensions, battered pile extensions, and you see closer, you see the damage at the top. Okay, so this bridge moved around a lot. Sonoma Creek was held with the new pile column extensions, okay, and that displacement was much smaller. These 2 bridges, this one and this one, they are very close to each other. You can see one from the other, okay, but the same era bridge, one retrofitted, one not retrofitted, and this one had to close. And that's our investment into bridges, okay? So, comparison and conclusions. Basically, we are learning from earthquakes. We have learned a bunch of things. No one knows, maybe in the next earthquake there will be something new that we have not addressed, I don't know. But laboratory testings are promising. Caltrans is willing to invest. We have invested quite a bit, and we will keep investing into these laboratory testings because that's the only proof we have. We don't want to really wait for the next earthquake, but we don't have much of a choice. It's going to come and it's going to shake most of the bridges. And cast in place is our practice. Precast is coming along, and new technologies will improve post-earthquake performance. Thank you.